In this video, we'll be looking into reactions of alkanes, specifically into free radical substitutions of alkanes. In reaction of an alkane with halogen atom, hydrogen atom of alkane is replaced by a halogen. So reaction is substitution reaction. Energy is provided by either heat, indicated by a capital Greek letter delta, or light, that's indicated as h nu, which is expression for energy of electromagnetic radiation. H nu is organic chemistry symbol for light, usually ultraviolet light actually. And just to remind you, halogens, general symbol X, are fluorine, chlorine, bromine, and iodine. And while in theory we state that all four halogens react, actually that's not quite the case. Fluorine does react, but this reaction with fluorine is very vigorous. It's actually an explosive reaction. And complex mixture of products is formed with substrates more complex than methane that have carbon-carbon bonds. Even carbon-carbon bonds begin to break, and we cannot control this reaction, so we cannot control which products are obtained. So for that reason, this reaction is not reparatively useful. Reaction with chlorine works very well, and we obtain corresponding products, corresponding chloroalkanes in good yields and reasonably good purity. Reaction with bromine also works very well, and again we get corresponding products in good purity. Finally, reaction with iodine actually doesn't work. Carbon-iodine bond is very weak, and reverse reaction would actually be favorable. So there is no reaction here, and this is an exception. This is actually a limitation of the method. So in conclusion, only substitution reaction with chlorine and bromine provides useful results. Reaction with fluorine is too vigorous, and reaction with iodine does not work. Now we are going to examine a mechanism of free radical halogenation, and we will do so on example of halogenation of cyclohexane with bromine. Free radical halogenation consists of initiation, propagation, and termination steps. So first, reaction is initiated in an initiation step. In the initiation step, free radicals are generated. So among the species that are present, the weakest bond is broken. In this case, that's bromine-bromine bond. So under the influence of heat or light, bromine-bromine bond is broken to give bromine atoms or bromine radicals. Keep in mind that while we add substantial amount of bromine to the reaction mixture, if we want monosubstitution, we will add alkane and bromine in 1:1 molar ratio, but only very few bromine molecules are homolytically cleaved into bromine atoms or bromine radicals. Frequently less than 1%, even maybe 1 in 10,000. So most of the bromine molecules remain intact. Very few radicals are generated, but that's sufficient to initiate the reaction, to start the reaction. And then the actual reaction, the actual substitution, occurs in propagation steps. So bromine radical, being unstable, will cause carbon-hydrogen bond to break. And it will cause carbon-hydrogen bonds to break homolytically. Homolytic breaking means that hydrogen takes one electron from the bond. That electron pairs up with unpaired electrons of bromine to give a stable molecule of hydrogen bromide. Remaining electron remains with carbon atom to generate new radical, and that radical is now carbon radical. That's the first propagation step. This carbon radical in the second propagation step reacts with one of the unreacted bromine molecules, which is most of the bromine that we have put in reaction mixture. So this carbon radical will now cause bromine-bromine bond to be broken homolytically. As it's broken homolytically, each bromine atom leaves with one electron. One of the two bromine atoms will pair up with carbon electron to form carbon-bromine bond. Remaining bromine atom will remain with unpaired electron. This one now goes back into first propagation step and reacts with another molecule of cyclohexane, and this cycle keeps going, or reaction keeps propagating for as long as there are materials present to react. Once we run out of reactants, reaction ends, and free radicals being unstable terminate in termination steps. And here are examples of termination steps. So in a termination step, two radicals will encounter and combine to give a stable molecule. So one termination step involves cyclohexyl radical reacting with bromine radical to give cyclohexyl bromide. Note that this is the same as the actual reaction product. So we cannot distinguish between a cyclohexyl bromide that was generated in the propagation step and one that was generated in termination step. The only thing is we can conclude that it's most likely generated in propagation step because most of it, more than 99%, is generated in propagation steps. Very few of cyclohexyl bromide molecules are a result of termination. Next termination reaction is very important. It's formation of dimers. That's characteristic for a free radical reaction, for non-polar reaction. If this were a polar reaction, then intermediate would have been charged, or at least have partial charge, partial positive or partial negative. And of course, two identical intermediates would have identical charges and would repel each other. So they could not combine to form a bond. Only free radicals can combine like this to form a bond. Dimer means that there are approximately twice as many atoms as in the starting material. Starting material being cyclohexane. So we get, in this case, dimer of cyclohexane, and that's an indication that a reaction mechanism is free radical. So in general, when we can isolate small amounts, typically 2-3% of a dimer, so byproduct, then that's indication that reaction proceeds through free radical mechanism and not ionic mechanism. And finally, two bromine radicals could combine to give bromine molecule. But that's starting material for the reaction, so that's not really termination. That one would simply go back into propagation steps and be used up in the reaction. Monosubstitution, which means single substitution, replacement of one hydrogen with one halogen in simple alkanes, such as methane, ethane, or cyclic alkanes, cyclopentane, cyclohexane, can give only one possible product, because all the hydrogens are identical, and replacement of any of those hydrogens gives only one single product. But as soon as alkane gets just slightly more complex, there is possibility for formation of more than one product. So we can see that an example of propane, or as in this case, butane. So we can identify two types of hydrogens. They are shown here in different colors. We can identify 6 primary hydrogens and 4 secondary hydrogens. And so in a chlorination reaction, replacement of any of the 4 secondary hydrogens is going to give 2-chlorobutane as the product, while replacement of any of the 6 primary hydrogens is going to give 1-chlorobutane as the product. If those hydrogens are replaced at random, so without preference, then calculated yields, expected yields would be 40% for 2-chlorobutane and 60% for 1-chlorobutane. Simply 4 secondary, 6 primary hydrogens, so 4 to 6, so calculated yields would be 40 to 60. These two isomers, they are isomers, of course, because they have identical formula, different molecular formulas. So these two isomers are called regioisomers, because the only difference between them is that position of functional group, in this case chlorine atom, is on different carbons. So different position of functional groups, those are regioisomers. If reaction produces different regioisomers in such a way that one isomer is produced preferentially over the others, then reaction is regioselective. If it does not, if they are generated at random, then reaction is not selective, specifically not regioselective. So we have to carry out experiment and see whether regioisomers are produced in expected ratio or not. In this case, we can see after the experiment that 2-chlorobutane is produced in 72% yield, while 1-chlorobutane in 28% yield. So reaction is regioselective. Regioselectivity is not very high, but nonetheless reaction is regioselective. So product that should be minor product, 2-chlorobutane, that should be produced only in 40% yield, is produced in 72% yield. That's a noticeable difference. And of course, 1-chlorobutane should be major, but actually it's produced in only 28% yield. That means that secondary hydrogens are more reactive than primary. They are being replaced at faster rate compared to primary. That's the only way how we can obtain more 2-chlorobutane than 1-chlorobutane. And we can calculate by how much secondary hydrogens are more reactive compared to primary. And here is how we carry out calculation. We take first total yield of replacement of all secondary hydrogens, and that's 72. we divide that by number of secondary hydrogens. So 72 over 4, that gives us 18, which is yield per one secondary hydrogen atom. And then we also want to look at yield per one primary hydrogen atom. So total yield of replacement of all 6 primary hydrogen atoms is 28, divided by number of primary hydrogen atoms 6, that gives us 4.67. So yield per one secondary hydrogen is 18, per one primary 4.76. When we divide the two numbers, we get 3.9, which means that secondary hydrogen is 3.9 times more reactive than primary. It's being replaced 3.9 times faster than primary hydrogen. So intrinsic reactivity ratio, primary versus secondary, is 3.9 to 1. So if we assume that reactivity of primary hydrogen is arbitrary number 1, then reactivity of secondary hydrogen is 3.9. Intrinsic reactivity ratio is important not only for theoretical purposes, where we can find out how much one hydrogen is more reactive than other, secondary versus primary, tertiary versus secondary, tertiary versus primary, but also for practical purposes, because we can use intrinsic reactivity ratio to calculate expected ratio or expected yields of the products. So we can again look at the same compound, butane, so 6 primary, 4 secondary hydrogens, and now look at different reaction. So it has been determined in experiments that in a bromination reaction of an alkane, intrinsic reactivity ratio of secondary versus primary hydrogen is 72. So secondary hydrogen is 72 times more reactive than primary towards bromination, which means that bromination is obviously much more selective compared to chlorination reaction. Now we can use that information to calculate expected yield of 2 bromobutane versus 1 bromobutane in a bromination reaction. And here is how we would do that. We calculate that by using number of secondary hydrogens, that's 4, multiplied by reactivity. So 4 times 72, that's going to be total amount of 2 bromobutane. And then divide that by total number of expected formation of 1 bromobutane, which is 6 number of primary hydrogens, multiplied by reactivity, 1. Because if intrinsic reactivity ratio is 72, we only list it as 72. That means 72 to 1. Secondary versus primary is 72 to 1. We simply ignore 1, list it as 72. So when we divide the two numbers, we end up with 48. That means that 2 compounds, 2 bromobutane and 1 bromobutane, will be formed in ratio of 48 to 1. Or when you recalculate that to percentages, expected yield is 98% 2 bromobutane and 2% 1 bromobutane. And that's actually what was found experimentally. So that shows that this method is correct. The reasons behind high reactivity of secondary versus primary hydrogens and actually tertiary versus secondary is in higher stability of the intermediate radicals. The more stable radical forms more readily or faster, and that's why there is higher intrinsic reactivity ratio of secondary versus primary, tertiary versus secondary hydrogen atoms. And here is the order of stability of radicals. So vinyl and methyl radicals have very low stability, about the same. Primary radicals are a bit more stable than methyl, then secondary were more stable, and tertiary the most stable. Now, if a radical has neighboring pi bond, such as allyl and benzyl radicals, they are exceptionally stable. They're actually much more stable than tertiary, which means that in a free radical substitution, those radicals will readily form and will form preferentially to any other radical. In fact, they will form to exclusion of all radicals, and they will give the only product. So in this case, we don't need to worry about intrinsic reactivity ratios, because typically only one single product forms as a result of a reaction. And so here is an example. Ethylbenzene, upon bromination, gives only one product. And that's product where bromine replaces benzylic position. Benzylic position is carbon that is directly attached to benzene ring. So only benzylic substitution occurs. Note that no substitution of methyl group occurs. And here is another example where we have competition between benzylic position, and that's carbon attached to benzene ring, and tertiary carbon, that's carbon next to it. And again, only benzylic carbon is replaced. There is no replacement, no substitution of tertiary carbon if we carry out reaction carefully and at temperature is low enough. So benzylic and allylic hydrogens are the only ones that are replaced. And so you're not looking at competition between different reactions. You're not considering intrinsic reactivity ratio, only whether a hydrogen that is being replaced is next to a pi system, next to a pi bond. And this brings us to allylic bromination of alkenes. Previously, or we have just seen benzylic bromination. So allylic bromination is position next to a double bond. So as you can see, only allylic substitution occurs. Now to carry out this reaction, we have to use one equivalent of bromine and carry out reaction under basically high dilution, very low concentration of bromine. If we were to use higher concentration of bromine, bromine readily adds across a double bond. So in this case, excess symbol means that we are using excess bromine. So we will end up with both substitution and addition, and that's usually not desired product. So we can carry out, so to avoid that, we carry out reaction under low concentration. But more commonly, we use a specific reagent. That's N-bromosuccinimide. So this reagent, upon irradiation or heating, will provide free radical bromine, but it does not add a cross double bond. It only provides free radical bromine. So in this case, the only product is substitution. Alternative or corresponding reagent for free radical chlorination, allylic chlorination, is N-chlorosuccinimide. You need to know those two reagents from their formulas. So you need to know their formulas. You need to know their names, N-bromosuccinimide and chlorosuccinimide, and you need to know them by abbreviation. N-bromosuccinimide as NBS and N-chlorosuccinimide as NCS. In reactions, in equations, we often use abbreviations. We can use any of the three. We can use formula, name, or abbreviation, but we frequently use abbreviation. And so, as you can see in this case, reaction of 1-butene with NBS in presence of ultraviolet light gives as the only product 3-bromo, 1-butene, and succinimide is undesired byproduct. We throw that away. This completes our study of free radical substitutions of alkanes. Next is introduction to unsaturated hydrocarbons.